All right, appreciate it. All right, go ahead, Andrew. What's going on, my
Yeah.
man?
Yeah. Oh, and just everyone remember, someone has to stay unmuted for some reason.
I noticed that real quick.
Yeah.
You
Yeah,
start
it does
going
that
real
on
quick.
every channel I go on, and I don't know why. Anyways, um, so the topic I wanted to discuss was, I think, one of your favorites, SFT, on genetic entropy. Um, and I've looked at it more and more recently, and the more I look at it, the more serious issues it has. Um, and one of these I kind of want to start off with, which is kind of a what seems to me to be a contradiction in terms. So according to genetic entropy, um, most mutations are effectively neutral, but at the same time slightly deleterious. And in population genetics, that is not possible simultaneously. Could you clarify if that's your correct way of saying it or whatnot?
So, if I'm understanding you correctly, you're saying it's contradictory to have most mutations deleterious and also unselectable at the same time, or
Yes.
maybe. Okay, so I am understanding that correctly. Well, I disagree because for a number of reasons. Skylet, if you could maybe share my screen real quick. Um,
And then I
it's
can maybe
pretty
go into
well,
the reasons why I think it's
yeah, yeah,
contradictory.
and that's fine. But it's not like this is made up by young Earth creationists. It's pretty well widely accepted by population geneticists. For example, here's a quote from a paper, The Distribution of Fitness Effects of New Mutations. They point out it seems unlikely that any mutation is truly neutral in the sense that it has no effect on fitness. All mutations must have some effect, even if that effect is vanishingly small. So, however, there is a class of mutations that we can term effectively neutral, because oftentimes I'll use that term, effectively neutral. No mutation can be 100% neutral to the perspective of the phenotype, right? They got to have some effect, even if it's small. Um, and I'm getting that from secular population geneticists. And then the other one, here's Kimura himself in a paper. He points out, under the present model, effectively neutral, but in fact very slightly deleterious mutants accumulate continuously in species. So this position that most mutations are deleterious and there are a certain class that are effectively neutral, they're unselectable. That comes not from young Earth creationists, but as you can see from secular population geneticists. Go ahead, Andrew.
Well, I think there's a difference to be made between saying it's effectively neutral and unselectable. Because however remote of an effect a mutation has, it's going to be acted upon by selection, even if that effect is very small, and that's why they call it effectively neutral. Um, in order for a mutation to accumulate in a population, in that sense, it would either have to be extremely beneficial, or it would have to be completely neutral, basically, or very, 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 very close to being neutral. Um, and in order for that to be the case, so that's what it takes for these mutations to accumulate. However, you're saying that most of these mutations are in fact have a slightly deleterious effect, um, and that means that they cannot accumulate because they hinder the survival and reproduction of the individuals that possess them, even if it's by a slightly tiny amount. It means that they're going to contribute less to future generations than individuals with more beneficial mutations will.
Right. So good points. I appreciate it. That's where I would disagree, and that's where I believe most population geneticists would disagree as well, is the fact that most of these mutations are only very mild when it comes to their effects, when it comes to their deleterious effects. As Crow points out, it usually has no overt effect, but shows up as a small decrease in viability or fertility. So the point is, when we speak of effectively neutral mutations, what we're saying is they're neutral to the perspective of selection. Selection can't see them because selection can only see the worst deleterious mutations. For example, a zebra is born with 3 legs, or born with one of their legs is bigger than the other 3, whatever. So some big mutation that's noticeable. Well, that's going to be the first zebra that's caught by the lion. Okay, to make it understandable, that selection is going to remove that zebra out of the equation. So the big mutations, right? There's some single point mutations that can literally kill an organism. Okay, so that organism is not going to have kids, is not going to pass on its genes. Okay, there's also the rare beneficial mutation, like sickle cell anemia, or a ton of examples that we can go over. The melanoprotein is one I was trying to think of there. So selection may be able to amplify some of these good mutations, which is like 1 in a million. But the point is, the majority are effectively neutral, as in they're only slightly harmful, but they're also unselectable. They build up. So you're saying that they could be removed. If they're just a little
I'm
bit
not
harmful,
saying they're. I'm not necessarily saying they will be removed. That's not what I'm saying.
Okay, well then if they're not removed, then what you're going to have is exactly what Crow points out here. The decrease in viability from mutation accumulation is some 1 to 2% per generation. So that puts shelf lives on the human. That puts a shelf life on the human genome. Is my point? Is we can only handle so many mutations. Yeah, go ahead. I'm sorry.
The fact is that humans, however, are an exception to the rule. They experience what Crow and Contra shape. Yes, relaxed selection, basically, right. And that assumption cannot necessarily be applied to all species. That's what they were concerned about, and I don't think it necessarily follows that, again, they can be unselectable.
Well, then how far back? Well, how far back can humans go given the mutation rate, 100 per person per generation?
I don't know if that mutation rate, for example, would apply to us in the industrial age as much as in the primeval age, basically. So I can't answer that question.
Well, if we were to start from the biblical model, where we have increased or better longevity in the past, and we I could show you a chart here, but I also wanted to make a point on the I'll go to that later. So my point is, and what you're saying is, yes, humans have relaxed selection because we're living in a time where we are taking care of our sick. So where in the wild a mutation would result in death and the non-reproduction of XYZ organism, when it comes to humans, we may be able to pass on those genes because of medicine and because we take care of each other, for example. So as Higgins and Lynch point out, we find that the accumulation of new mildly deleterious mutations fundamentally alters the scaling of extinction time, causing the extinction of populations that would be deemed safe on the basis of on demographics alone. So here's my point with what he's saying here. Yes, we have relaxed selection in the human population, so we will degenerate faster because selection is relaxed and more mutations will accumulate. But that doesn't change the fact that most mutations are still effectively neutral, even in non-human species. Now, in the wild, there's better selection, okay, where selection will essentially remove the worst deleterious mutations. I get it. So at best, what you have in the wild, Andrew, is extinction being slower, or genetic sickness being slower, but still the genetic sickness is still inevitable because we still have effectively neutral mutations, but selection's a little better. So species in the wild might last longer than humans. That's the best you have. Yeah, go ahead. I spoke a lot there, so take your time.
Yeah, I think that's where we disagree, because I think selection is what happens at the end of the day, not necessarily a conscious force as picking and choosing here and there. When you say selection can only select out the worst of these mutations. I think that's kind of the opposite of what selection does. What it's really doing is selection is what we call it when we have variation in differential reproductive success. My bad. And that's what we have at the end of each generation. So it's not so much a big thing of you're getting at extremes as much as it's more like a gradient basically. And I'm not saying that these slightly deleterious mutations will necessarily be removed just like that. Rather, I'm saying that they cannot accumulate because they're going to leave they're going to be slightly less fit, however remote that is, and that means that in the next generation and the following generation.
Are we talking about human species or non-human species right now?
I guess non-human species.
So would you agree that man is essentially degenerating to the point where genetic sickness is unpreventable? Selection may be able to slow it down, but we are getting worse essentially. Or would you say
that kind of gets into other mechanisms that kind of defeat the purpose of genetic entropy, such as back mutation. Yes.
Well, here's the thing. Even Dr. John Sanford here at the NIH, he spoke on back mutations. That was one of the criticisms that was brought up in the Q&A, and he pointed out that back mutations are much too rare. And by the time you ever had any real solution based on back mutations, we'd be pretty well driven to the point of no return. And as you can see here on this slide, I mean, Haldane, Kimura, Lynch, they've all pretty well pointed out exactly what I'm saying, that the mutation rate is high. It's going to eventually lead to rapid degeneration. Near neutrals should be virtually unstoppable. I mean, Oda, Kondrashov, Crow, Kimura. I mean, these are all non-young, other than Sanford. Sanford's a young Earth creationist. But beneficials don't work. Back mutations don't work. Synergistic epistasis doesn't work. Mutation count mechanism doesn't work. So, I mean, are you going on record saying that there is? Would you agree that man is not getting better, at least genetically?
I guess so. I have no problems with that.
See, here's the problem with what you're saying. So are you pretty well, if I'm understanding you correctly?
If it's okay, I'd like to respond to something else you said.
Yeah, go ahead. I said a lot there. Take your time.
Because, for example, if Sanford is claiming that back mutations are too rare, that's, from what I understand, mathematically impossible, because the more mutations that say just for simplicity, in this case, a C to a T is deleterious, and you have more C's to T's, that necessarily means that C to T is out of the picture. You can't go from C to T to C to T, which means that going from T to C has to be beneficial. And since there are more C's to T's, that means that T's to C's has to become more prevalent, ergo, more beneficial outcomes or beneficial mutations. So I don't quite understand how we can say that back mutations are rare enough, because they clearly become more common as you go through mutation space.
Right. I get what you're saying. And unfortunately, and correct me if I'm wrong, this has not yet been demonstrated as a possible solution from the evolutionist side, but from the perspective that man is degenerating, mutations are accumulating, and this puts a shelf life on the human genome. People like Dr. John Sanford, people like Dr. Rob Carter, they have done extensive numerical simulations with biologically real parameters. And what they've discovered is that whether you look at back mutations, whether you look at synergistic epistasis, whether you look at mutation count mechanisms, whether you look at super beneficial mutations, you name it, all you ever get at best is selection slowing down the degeneration process. And this is with very generous parameters, sometimes unrealistic, as in let's just give evolution the benefit of the doubt and we still never see a resolution to the genetic degeneration problem. Now, I could be wrong. Has your side looked at that? Have they done numerical simulations? Have they done anything to actually show that back mutations can solve
I
the
don't
problem?
think we need to, because we haven't necessarily observed any cases where these simulations have borne fruit.
Sure they are.
Well, okay. Are there any observed examples of error catastrophe in the wild?
Oh, error catastrophe?
Yes.
Oh, big time. Yeah, I mean, I can show you a bunch of
Yes,
slides.
you have things like cheetahs, for example, and they're not going extinct.
Yeah, cheetahs are going extinct. They're down to, I believe, 7,000 the last time I checked. For the longest time, it was 10,000. Now they're down to 7,000. Their sperm's highly degenerate, and conservationists are incredibly worried about the extinction of cheetahs.
Well,
We have
they should be already extinct, however.
no. What that would indicate is that cheetahs just haven't been around long enough for the eventual degeneration, given their numbers and given the amount of recessive mutations that have come to the forefront.
Okay.
There's also butterfly populations. There's also I'm trying to find it here in my slideshow. Mammoth populations. They were seriously inbred. They suffered from mutational meltdown, error catastrophe. Same thing with a lot of the so-called hominid species, right? Floresiensis, Neanderthalensis.
So here's the question I have there. In any of these cases, where any of those populations that went extinct, were any of them equivalent to the sizes of populations we see now?
No, that's a good question. That's the whole point, is small isolated populations, they will go extinct quicker because typically isolated right. Oh, exactly. Especially because you could have the rapid accumulation of new mutations, and you'll have I found some of these papers. I will share a screen for you. But
I will note, however, that is for extremely small populations.
Yeah, but you said any examples of error catastrophe. That's exactly what this is. So, Scout, if you could screen share. So we have high genetic load in isolated butterfly populations. Right here, examples of fitness reduction in small isolated populations include many mammals, reptiles, amphibians, natterjack toads, European tree frogs, rattlesnakes, the cheetahs, mammoths. Look, dying woolly mammoths were in genetic meltdown. So what this is mutational meltdown in small isolated populations, a lot of times due to inbreeding. But humans exist in a larger population. So it's kind of like you guys point to microevolution, macroevolution. Okay, you extrapolate micro to macro. What we see in these small isolated populations that experience genetic meltdown, this is like micro genetic entropy. This is a sneak preview into where larger populations are going genetically as a species. This is where we, as the human population, we have about 7 billion people on the planet. This is where we are going.
Well, you mentioned that these populations are going extinct through inbreeding, for example.
Right.
But that's not necessarily behind the mathematics of the standard genetic entropy model according to Sanford.
Well, no. So, for example, here in the Mammoth paper, we observe an excess of detrimental mutations consistent with genomic meltdown. Okay, we observe an excess of deletions. We actually see that in the human population. I mean, the average, I think Kondrashov points out, the average human has, in the thousands of negative broken genes. Okay, an increase in the proportion of deletions affecting gene sequences, the excess of premature stop codons. The point is a lot of defective genes. Now, these are going to accumulate quicker in small isolated populations. Yes, I agree with that. Of course, it's going to take longer in larger populations, but it's still inevitable. It's still going to happen. It's just a slower process. Now, here's the thing. I'll point out this, and then I'll let you go. Is if we were to look at some of these so-called hominids, okay, let's say the hobbits, Floresiensis. Well, they got isolated like Naledi and Luzonensis. They got isolated on islands. So they experienced rapid genetic degeneration because they were a subgroup of people larger population of people, then you have a subgroup, they become isolated, they begin inbreeding, and they experience rapid genetic degeneration as a subgroup. But that doesn't stop the degeneration of the larger population. It's just going to take longer for the larger population to degenerate due to mutation accumulation. Go ahead, Andrew.
Well, it seems to me like you're equivocating extinction vortex with air catastrophe, because like those are different mechanisms, like you said, where a small population goes extinct because of genetic drift accumulating these deleterious mutations, whereas in these larger populations, this kind of gets back to the idea that on average, populations that we see now should have a terminal decline in fitness, and that they don't.
We see that. We see that, though.
Okay, where?
If we talk about, okay, first off, before I go to the slide where
you can't use humans, because humans, like I said, are an exception. They're not applicable to the same populations.
They're an exception when it comes to the fact that they have relaxed selection. But populations in the wild, although selection is better, it still doesn't change the fact that effectively neutral mutations are invisible and build up. For example, if you have a population, okay, but here's the thing, you were the one just arguing that there could be a solution to human genetic degeneration. You still haven't fully tapped out on that. So before we even go to the
don't think I said that.
Well, you said back mutations could possibly reverse the genetic degeneration in humans. Did you not? Or were you referring?
I don't know if I would say reverse. You can reach an equilibrium point. Possibly.
No, the equilibrium doesn't, because by the time you reach an equilibrium, what you're going to have is genetic sickness to the point where that's it. It's too late. I mean, even now we see accumulating diseases in terms of immunological diseases, mutation-related diseases, whatever. But here's the thing. Okay, mutation and human exceptionalism, our future genetic load. If every single newborn has 100 new de novo mutations, Andrew, that means you have 100 new mutations. I have 100 new mutations. Sky Out has 100 new mutations. Some guy over in Australia, some guy over in China, he has 100 new mutations. So the point is, it's not like this is just isolated cases of 100 new mutations. No, it's the entire planet of 7 billion people that are experiencing this genetic load. Every single generation is more mutant than the generation before it. So are you just going to remove every single mutant, which would be every single person?
What do you think about that, Rational? You're going to keep slapping and running? I'm just kidding. Go ahead.
I like talking to Andrew.
I'm joking. I
will say this in terms of compliments with Andrew. Andrew and I could talk for hours and hours as we have, because Andrew, I really respect the fact that he engages the data, goes back to the drawing board. He'll look for rescue devices. Just kidding, Andrew. But what I find with a lot of the theistic evolutionists is they don't even want to engage the data. They don't want to use critical thinking. But I do find Andrew at least does that. But anyways, yeah, I did make a point there, Andrew, that the entire population is multiply mutant. This would also apply to species in the wild. If you have a population of, I don't know, what do you want to look at? Elephants? How many elephants in the world, Andrew?
I wouldn't know off the top of my head.
Well, here's the thing. Same thing with elephants. Every single elephant, okay, is more mutant than the generation prior to it, more mutant than their parents, their grandparents. So the same thing still applies. Whatever.
So you're talking about Muller's ratchet in this case, right?
Not necessarily. No, not necessarily, because I'm just talking about the rate of mutations that accumulate from generation to generation.
Due to sexual recombination, you're going to have individuals with on average less bad mutations than the previous generation. That's just how swapping and mixing the genes works.
Wait, repeat that part that you just said about recombination.
Like, I mean, it means that in some circumstances you're going to have individuals from the previous generation, or I should say from the parents of the previous generation. You're going to have offspring that some of them are going to have fewer bad badness basically than
Well, wait a
than
minute,
the previous generation.
No. If we're accumulating, let's say with humans, 100 new mutations per person per generation, that means I am going to have more mutations than my grandparents. My kids are going to have more mutations than me. How would that not be the case?
Well, in that case, well, you're not differentiating between different types of mutations in that case. Because you admit that not all of them are harmful mutations. It can't be.
But right here, Kimura, effectively neutral, but in fact very slightly deleterious mutations accumulate continuously in every species. See, here's the thing. Kondrashov calculated that out of the 100 new mutations, where's that paper? Right here. Out of these 100 new mutations, okay, he calculated that 10 of those are deleterious because he holds to this idea that only about 10% of the genome's functional. So therefore, 10 of those would logically be deleterious. But if the genome's 20% functional, 30% functional, or 80% functional, as the evidence seems to suggest, that means you have up to 80 of these which are deleterious. Kondrashov recognized that it was a problem even if the genome's 10% functional and only 10 are deleterious. But now we know that a lot more of the genome's functional than 10%, which means the degeneration problem is even worse. So the point is, no, you're still getting enough deleterious mutations, Andrew, that are effectively neutral, that aren't selected, that are going to create loads and loads of problems. And here's the last thing I'll say, and I'll yield, and you take as long as you want. When it comes to the biblical starting point, okay, to bring this all the way back to what I was saying 15 minutes ago, when we start from the Bible, we can actually plot the biblical lifespan starting from Adam, okay, Adam, Seth, whatever, down to after the flood. And we see the same exponential decay curve based on what we know about accumulating mutations. We see the same exponential decay curve in biblical lifespans as we do in biology. And when we actually do a coefficient p-value, for this to be a coincidence, okay, it's all been graphed out, this would be less than 1 chance in a quadrillion of being true, as in for the biblical authors, early biblical patriarchs to make this up, to perfectly fit what we know about mutation accumulation, they would have had to have advanced knowledge in biology, genetics, and mathematics. Now, I don't have enough faith to resort to that argument. So my point would be, why, if this fits so nicely with the biblical model, why should I then believe your model? Yeah, go ahead.
Well,
go ahead.
Well, I mean,
why should I believe your model?
Well, because it seems likely that, okay, you're starting, genetic entropy is starting in a perfect starting point in terms of the genome is concerned.
No, you don't have to. It can start at any starting point.
But you're saying the original starting point was perfect, was it not?
Well, from the Bible, but I mean, you could, like, for example, they've done numerical simulation experiments where they have, and I actually have an answer to this objection somewhere, but since I have 1,000 slides, I'll give up. But the point is, they've done numerical simulations, Dr. John Sanford, a number of geneticists, where they have pointed out, okay, let's start with this.
To talk about.
Yeah, go ahead.
Well, Mendel's accountant, for one thing, doesn't take recombination to account. I'm not saying that necessarily gets rid of genetic entropy, but it does mean that the models they're using are unrealistic.
No, they are realistic. And many of them have been published in secular papers, in secular journals. For example, the waiting time problem, that was published recently in a secular journal. That's been read by over 10,000 scientists, hasn't been refuted or criticized. So am I going to believe some blogger that says, Mendel's accountant, it's a horrible program? No, because it's made its way through the peer review process. It's literally the most sophisticated program at simulating evolutionary processes like natural selection. I think you're thinking about you are thinking about the waiting time problem with recombination, but recombination would give such small beneficial effects, it wouldn't even come close to solving the problem. But my point, I'll say this, and I'll let you
data to back that up.
Oh yeah, I can back that up for sure. It was addressed in the waiting time problem paper.
And where was this
by
published?
Stanford? He had a section on recombination in that. I can pull it up if you want, but I just wanted to point out your error that we have to start
was
with
this in his
genome.
book, or was this published in a peer-reviewed literature? Is what I'm asking.
In the peer-reviewed literature, I'll pull it up for you, my good man. But my point is, yes, from the biblical starting point, we start with perfect genomes. Okay, but you don't have to start with perfect genomes when you're considering genetic entropy. You can start at any fitness level. You can start with any number of mutations, and from that point forward, you still get an accumulating genetic load. From the biblical starting point, yes, 0 mutations. That's how we plot out the biblical lifespans, but we don't have to do that, as in it doesn't change the outcome, is what I'm saying. Go ahead, Andrew. Take as long as you want, because I'll have to pull up this paper. So,
well, I mean, because I think this gets back into. Oh, wait, 1 second.
Take your time, man. Do your thing. Yeah, appreciate everything you guys are saying, man. Appreciate SFT's time and everything. And A Rational Empiricist, thank you for showing up and everything for the after show. I'm getting a lot of good feedback in the community now.
Did you just call him irrational empiricist? Just kidding. Anyways, I just read through this paper recently when I was refuting Dodgeball Dan, so I've got it ready now. So Here it is. Okay.
Go ahead.
So have a look at this. This is the paper. Okay, waiting time problem still has not been solved. Here we go. Recombination may help reduce waiting time. That was Andrew's argument. This is directly in the paper. Okay. Let me see here. The probability that a crossover might occur between two specific adjacent nucleotides is extremely low, while a conversion event is only slightly more likely. Such rare recombination events should reduce the time to first instance of a target string, but only slightly, and only when the two recombining sequences are genetically distinct from each other. Because genetic drift within a small hominin population is so strong over deep time, any two recombining strings will in most instances be identical. This makes the overall effect, this is exactly what I was saying, this makes the overall effect of recombination within a string exceedingly small. In other words, we can pretty well just ignore it, laugh at it, and tell it to go and slap and run.
Well, for one thing, they're talking about hominin populations, which gets back to humans again. But for another thing, alleles, well, of course, you're not swapping individual nucleotides. However, what you are swapping are individual alleles. And some alleles, by chance, are going to have more bad mutations than others. And that means that when you end up with offspring that have alleles which just happen to have more bad mutations than other alleles, you're naturally going to end up with some offspring that have more good alleles than bad alleles, and that means that they will be slightly selected for. And that means that selection.
He told you, SFT.
How dare you slap and run, Skyo? See, here's the problem: is all you're ever getting is slight improvements, even with recombination, even with your best beneficial mutations, and these improvements are only linear improvements at best. That's why when we look to total functionality or absolute fitness, we still have a net loss. So that's
that's another thing. What does absolute fitness even mean?
Well, if we look at
a real concept.
Well, no, it's a real concept because reductive evolution is a real concept. You can see that in paper after paper. You can see that with bacteria, where you have, for example, you have a linear increase in fitness due to some beneficial mutations. But overall, like in Lenski's experiment, overall, we have shrinking functional genome sizes. We have degeneration. We have genes being lost. So what that is a loss in total functionality. It's kind of like my car. If I wanted temporarily better gas mileage, okay, I can do that. Let's start removing weight from the car. I'll tell Skyo to remove the doors, remove the side mirrors. Hey, Fans. Temporarily, we have better gas mileage, but overall, we have a decrease in functionality because
Why
we're
am I
pretty well
removing
just
doors?
That however
That's
ignores beneficial compensatory mutations.
Oh, come
I'm
on,
probably mispronouncing
Andrew.
that.
Now you're just going in circles. We've already addressed your compensatory mutations, beneficial mutations. They've been addressed. Your 1 in a million are still reductive. They're not going to do anything to help.
Those aren't the same as back mutations as we were talking about earlier, if that's what you're alluding to.
I never said they were. Back mutations don't work, and beneficial mutations don't work either. All you ever get
beneficial
is a
mutations
linear-
aren't the same as adaptive compensatory mutations.
Compensatory mutations is exactly what Snake was right and I debated about like 2 years ago, and that still doesn't work. That's been addressed in these numbers of papers. And your recombination, you're failing to account for mutations, Andrew, that are in linkage groups, because even your best scientists or whatever, CRISPR, Dan, they'll agree, because they try and use this against the created heterozygosity model, that mutations in linkage groups are pretty much linked forever. So if you have recombination, sure, but you still have lots of bad mutations in those linkage groups, and therefore the linkage groups are reducing in total functionality and fitness.
Sure, that's what we see in the Y chromosome, which doesn't do recombination. That's not what we see in other parts of the genome.
The Y chromosome, mitochondrial DNA, are non-recombining DNA compartments, but the nuclear DNA recombines.
Well, that's another issue. Why isn't the mitochondrial genome extinct at this point?
Because, as I pointed out earlier, the accumulating mutational load puts shelf lives on genomes. So the fact that what we see in real time in pedigree studies and in the studies that measure the rate as to which mutations accumulate in the different DNA compartments, this means, okay, there must be shelf lives on genomes, which means humans cannot go back that far, and non-human species cannot go back that far either, especially when we look deep within the geological column. Say you go a few 100 million years to like I don't know, horseshoe crabs or something. There's very little change. But what we know about mutation accumulation means that these horseshoe crabs or coelacanth or whatever, they could not have been around for the claimed 300 million years, or else they would have been extinct because of what we know today about the mutation rate. So answer that question about the linkage groups. If mutations in linkage groups are pretty much linked forever, Andrew, okay, and you have all these bad mutations in these linkage groups, and then let's say you get, I don't know, 1 or 2 beneficials, or you get some rounds of recombination. Okay, how's that ever going to solve the problem that these bad mutations are still linked? As in, you can't get them apart, minus some rounds of gene conversion. Yeah, go ahead.
Again, we're assuming that they're staying in that nucleotide state forever. We're assuming there are no back mutations in this region of the genome.
In linked regions?
Yes.
So you're saying bad mutations in linked regions are going to experience back mutations, and
I mean, that happens in other parts of the genome,
So are you proposing this for humans or just non-human species?
It shouldn't matter for any species as far as I'm aware.
So is it your position then, after this discussion?
Can you come closer to your mic, SFT?
Oh, yeah, sorry. How's that? A little better?
Yeah.
Would it be your position then that humans and the genetic degeneration problem may be slowed by whatever means that we've been discussing, but not actually stopped? But in non-human species, it can not just be slowed, but it can actually be stopped. Would that be your position then?
I guess so, yeah.
Okay, and your evidence for this is...
Dogs barking in the background. Sorry about that.
That's okay. Hey, listen, dogs produce dogs, Andrew.
Oh, boy.
See, here's the thing that I find funny, okay, is we're talking here about mutation accumulation, the fact that we have this increasing genetic load, okay, really in all species. And I will agree that because of relaxed selection, humans will degenerate quicker than non-human species. But overall, mutations are accumulating. They're deleterious. Population geneticists acknowledge this. But evolutionists want us to believe that single-celled like ancestors evolved over time into whales, humans, monkeys, whatever, through mutation accumulation, since they look to mutation as the source for all genetic
down
diversity.
that route, SFT, because now we're getting into common ancestry.
Well, let me ask you this. If what we've been talking about is clearly demonstrating that mutations lead to disease, they lead to damage, they lead to
I don't think it's demonstrated that way. That's what I'm arguing against.
Well, then you're arguing against the opinions of your own population geneticists. I've shown you a ton of papers and quotes where they point out that no mutation can be absolutely neutral. They must all have some effect on genotype, even if that effect is vanishingly small. I mean, that's out of their own mouths.
That they don't say that's unselectable, therefore.
Yes, they do. What's the whole point of calling it effectively neutral? Neutral to what? Neutral to...
It means that the fitness effect is very small, but it doesn't mean it's zero.
If neutral,
there's any fitness effect, then selection is going to act on it.
No, that's wrong. That's wrong, and that's pure stupidity. I'm sorry. Listen, if a mutation's neutral, whether effectively neutral or absolutely neutral, what is it then subject to?
Well, in most cases, it would be it would be part of drift, basically.
Yes, yeah, exactly. Genetic drift. So if it's subject to genetic drift, then what's going to happen to populations over time? They're just going to accumulate more and more mutations that are effectively neutral, that are subject to genetic drift. And eventually, like we see with the human population, you have 7 billion people who are multiply mutant. I'm mutant. Skyote's mutant. Rational Empiricist, you're mutant. PMARS is very mutant. So let's say selection, let's say out of all 4 of us, let's say PMARS is the most mutant. Okay. Just kidding. That's kind of mean. Let's say I'm the most mutant. Okay. I'll put myself under the bus. Okay. Selection removes me. Okay, let's remove the worst mutant in this room. Now we're left with 3 people who, although less mutant than me, are still more mutant than the generations before them. So all we have is yeah, go ahead.
I just feel like you're missing out a big part of selection, which isn't just that individuals die off, but they can also leave a lesser effect on the frequency of future generations, which I think is even more important in this context.
No.
All right, let me jump in here, man. Let me jump in here for a second.
I feel like we're going in circles. I'm sorry.
Andrew, so since you still believe that banana plants and whales are related, then let me ask you a question, my good friend.
Okay.
Since you've now admitted that genetic entropy is a reality, I'm just kidding. I know you didn't, but you will one day, Andrew. You're seeing
maybe. I cannot deny that possibility. I think it's an unlikely one, but
because you're gonna listen back on our discussion there, and you're gonna be like, back mutations, beneficial mutations, synergistic epistasis, none of them work. So I'm just gonna have to tap out, believe the Bible. But no, in all seriousness, we had a good 45-minute discussion there.
Yeah,
so what I'll probably do as well, so Skyote, make sure you don't delete this stream. I'll maybe clip that out and just put it up on the channel tomorrow or something for people to listen to.
Yeah, feel free, man.
Something tells me if you're Speed's probably going to see this and we're going to go over this, so that's in all out likelihood.
Okay, there you go. I'll put it on my channel just to give them some content, because it's probably good for business. So anyways, in all seriousness, my doomsday friend, if I'm Superman, you're Doomsday then. If you're too young to know who Doomsday is, you can Google it. So since you love phylogenies, which I do too.
30 minutes, guys. 30 minutes. I'm wrapping this up.
What? Skyote? I thought you were going to be here all night.
No, man, I gotta get sleep too. It's getting late over here too, man.
Yeah, you're probably feeling tired too. Okay, well, it won't be that long. I am just curious then as
Yeah.
to your um, thoughts, and I've asked you this before, and since you like phylogenies, how do you like? What are your thoughts ultimately on the fact that? I mean, we could look to mitochondrial DNA or Y chromosome, whatever. I asked Rob this the other day, but if we map out worldwide genetic diversity and we see low genetic variation in mitochondrial DNA, we know the mitochondrial DNA is fast in terms of its mutation rate, then why don't we see tens of thousands of mutations here? Why are we only looking at in terms of the mitochondrial DNA, only 100 to 130 mutations, really, and
Okay,
in the Y chromosome, roughly a few
this
hundred.
is a little advanced for me, and a little out of my depth and out of my field. I do know a little bit. I do not believe that what you said earlier, like what a whale became a tiger, became a tree, became this and mutated. That's ridiculous. I do know a little bit about science, but I would say this is out of my field of expertise. But
yeah. Well, I was asking Andrew.
Oh, okay. Well, yeah. Go ahead, Andrew.
I wasn't going to try and I'm not going to try and put you on the spot, Kyle. I don't want to ask you.
You truly are an arch nemesis, SFT.
Yeah, no. I'm not throwing this at you, Scott.
This is over my head for a minute.
You might even.
I want to learn what you're saying, though, bro, so I can understand it. But I don't understand what you're saying. I have to go back and look at it.
Oh yeah, no problem. And that's okay. Well, here's the thing. There's a lot of people, and the last time I spoke to Smokey, unless he changed his mind, I don't know. But there are people who believe in an old Earth, an old universe, but young creation. So this would not be totally contradictory with your position, Skyout, if you were to hold to that position, an old Earth, old universe, but young, special creation of man. Because all this shows, and all I'm showing to the evolutionists is, okay, we have mitochondrial DNA, which takes us right back to one mitochondrial DNA ancestor, who we'd say is mitochondrial Eve. Okay. And then we have a one Y chromosomal ancestor, who, according to our model, would take us back to Noah, our last Y chromosomal ancestor. That's really all it's showing.
Okay.
And it's contradictory to the evolutionary model, because they want to not only say we're related to chimpanzees, but they also want to take the origin of humans back a couple 100,000 years to millions of years, depending on if we're going back to Erectus or Australopithecines or just the out of Africa. So that's it's more contradictory to the evolutionists.
Okay. Have you heard of this out of Africa theory?
Yes, and we can get into that, Scout, but I am curious as firstly, Andrew's thoughts on this, according to, because Andrew, and here's the last thing I'll say, and take as much time as you want. When I speak of separate ancestry, okay, and this is the topic I've written books on. When it comes to universal versus separate ancestry, as long as I can show, evidentially, that one organism is not related to the rest of the biological world. In this case, humans. I've got a lot of genetic data showing that humans are not related to anything else. They're not related to chimpanzees, who would apparently be our closest cousins. That destroys universal common ancestry, because now you no longer have universal, you have separate, where humans are separate from the rest of the biological world. They're specially created, is my point. Andrew, what are your thoughts? Take your time. I spoke a lot there, so.
Yeah, I guess if that were, I don't feel like that's the case, but if that were shown, I think it wouldn't necessarily show that all other organisms are unrelated, because some we know are related to each other, going back pretty far at least. The other thing I would say is, at least going back to the root of the tree of life, it gets a bit fuzzy because of things like horizontal gene transfer. And that's not to say that we can't figure out those through phylogenetics. It just means that maybe we need a different concept of phylogenetics going back that far.
Well, let's say Well, let's say hypothetically, humans are not related to chimpanzees and therefore not related to anything else. They're specially created. It wouldn't matter even if everything else was related. Even if you still wanted to say pine trees and whales were related, pine trees, whales, and chimpanzees are related, it still destroys universal ancestry, because now all plants and animals are not universally related because humans are now not in that tree of life. That's my point. All I need to do is really show you one biological organism that has not evolved through common descent, and that not only confirms special creation, it refutes universal ancestry, because you need humans to be related to chimpanzees. You need humans to be in that phylogenetic tree of life. Without humans in that phylogenetic tree of life, you don't have universal common ancestry. Does that make more sense now?
Right. I guess my response to that would be that in that sense, I don't feel that the concept you're referring to as universal common ancestry is really consensus at this point, because it's not at all clear if all life indeed follows a nice bifurcating tree of life. It may be more reticulate in some places.
Right. Let me correct myself. Yeah, let me just correct. Yeah, because even the evolutionists would admit that when it comes to the origin of eukaryotic organisms, or when it comes to bacteria, you have horizontal gene transfer, and therefore at the root or base of the tree, you have more of a bush. I understand that. But higher up on the tree, where you have humans and chimps and old world monkeys and dogs and just mammals and vertebrates, you would say that all mammals are related. I'd imagine you'd say all vertebrates are related. So higher up is where it's less messy for the evolutionists. So if humans are not related to anything, okay, and it's just kind of the human tree, then that would be a huge problem for common descent, would it not?
Well, I guess in this case, if we're I'm not sure how to address that, because I don't feel that we really know what we mean by universal ancestry at this point.
Well, would you agree with Darwin, where he said it's a fact that all life, including plants and animals, should be related?
I lean towards that view, but I don't think that's necessarily the case based on current data.
So would you say there were separate creations, but you don't believe in creation, so therefore separate origin of life scenarios that
I kind of only take it back as far as the root, like I was saying earlier. That's as far as I'm going.
Okay, so you take it, but you would admit, you would agree, as you just said, that all, at least vertebrates, are related.
Yes.
Okay.
Yeah,
okay,
that part of the tree I do think is a clear bifurcating pattern.
So you would agree then, I think, with evolutionary consensus, that there's universal ancestry among vertebrates.
Yes.
Okay. So if we were to show that humans, being vertebrates, being primates, if you go taxonomically speaking, and mammals are then not related to, let's say, other vertebrates like chimpanzees, as in they have a separate ancestry, therefore that at least ruins universal ancestry of vertebrates. That would
I feel like I get what you're saying, and I feel like I would agree, at least in overall. I just feel that it would be very difficult to show that without going back to phylogenetic methods.
Okay. So now here's the thing. We're looking at phylogenetic methods here. So if we look at I like the uniparentally inherited DNA compartments, because they're less messy. There's no recombination for the most part. So I like these types of phylogenetic trees. So my point is, let's look at a Y chromosome then, since we typically focus on the mitochondrial DNA. If we're not seeing tens of thousands of mutations, we're only seeing a few hundred mutations, as would be expected if the Bible's account of independent origins were true, right? Separate ancestry, God created male and female. but inconsistent with the universal ancestry model, at least the universal ancestry model of vertebrates, where there should be tens of thousands of mutations here. Then how do you explain this phylogenetic data according to your model? Are you just going to invoke a massive amount of purifying selection to remove all the DNA differences that should be there, or how would you explain it? What are your thoughts?
Well, I mean, I mostly deal with other parts of the genome and more morphology, for example. So I think at this point, whereas one does not know, one should remain silent.
Right. But my point is, okay, and I've had so many debates on this that I'm confident about it. Mitochondrial DNA phylogeny and Y chromosomal DNA phylogeny of humans, okay, demonstrates that we've only got a few hundred generations max. We know the Y chromosome and the mitochondrial DNA are vastly, vastly, vastly different than chimpanzee Y chromosome and mitochondrial DNA. You don't have tens of thousands of mutations in either the mitochondrial DNA or the Y chromosome. What we find is one Y chromosomal ancestor of all people on the planet, one mitochondrial DNA ancestor of all people on the planet, consistent with special creation. I don't see how this can fit into the universal common ancestry model. What would be your best way of incorporating this into your model then, Andrew?
Well, I guess at this point I would say that it might indicate a most recent common ancestor of these mitochondrial sequences, but it doesn't necessarily indicate the origin of them, is what I would say.
But so would you then put a Y chromosomal or mitochondrial DNA ancestor just a few thousand years ago then, based on the data?
I couldn't say, for example, that is when the most recent ancestor of humans lived, but perhaps I could say that's when the genes coalesce on the tree. Gene trees aren't always indicative of species trees, for example.
Because remember, these are, like, for example, this Y chromosome tree is Y chromosomes, not from just one group of people, subgroup of people, but from all people groups. This is all a reflection of DNA differences, a reflection of mutations over time in all people groups in terms of the Y chromosome here. And therefore, this would be the last Y chromosomal ancestor of all people. That's why we can look to various haplogroups. That's why I typically point to the HVR haplogroup here on the mitochondrial phylogeny. This is the most common one in Europe, and how we have evidence of people picking up more mutations in the exact same amount of time because of the length of the branches. So that actually ruins the evolutionary molecular clock, because if we have the same people living at the same time accumulating more mutations than, let's say, their cousins, then we can't really make assumptions based on when humans and chimpanzees, when their last common ancestor split, and then base our mutation rate that way, right? People like Dan, they want to look to what's called the substitution or phylogenetic rate, and they want to essentially base it off a much slower, not really a much slower mutation rate. They'll at least acknowledge that the mutation rate is fast, but they'll say that most mutations are lost, and therefore purifying selection has removed most of the mutation rates that essentially should be there, which I agree with. By definition, the pedigree-based mutation rate is faster than the substitution rate or the phylogenetic rate, because obviously a lot of mutations are weeded out over time, right? But even considering that, even considering massive amounts of purifying selection, it's like we're still looking at such low genetic diversity. And then, Andrew, as I pointed out before, the Y chromosome dissimilarity right here of humans and chimpanzees. Look what David Page said. The Y is full of surprises. The Y chromosomes of chimps and humans is horrendously different from each other. Horrendously. So it's not just a little different, it's a lot different. my point is, to sum it up, this is a problem for universal ancestry in terms of at least vertebrate ancestry. So I don't know. I don't want to beat a dead horse. If you don't have an answer now, we can certainly look into that. But
I definitely have to look
The
into
horse
that.
is still alive. SFT. No, I'm just kidding.
the horse. All right, I'll beat it a little bit more. I'm just kidding.
Finish him off. No, I'm just kidding.
Finish him.
He's just crawling.
You know what? I want to save this horse for future discussions in the future. So I'm gonna let him. I'm gonna leave him just barely alive. Let him heal, and then come back for more. Then we'll beat him for good.